Okay, so we know a bunch of trig integrals. Now we're going to see how trig works inside of substitution. So I know that I have a chain rule that tells me what to do if I have trig of another function. So I might be taking the derivative of this, and what I would end up with is the derivative of the trig function. So I'm going to kind of put as one word, derivative of trig of that g times g prime. So in other words, we still have this idea of an inside function that could show up inside of trig. And we've seen that when we're picking our u, a lot of times we want to pick it to be the g that shows up on the right side here. So another useful idea for picking u is to let u equal to the function inside of the trig function. Let's do a couple examples to see that happening. So we want to evaluate the following integrals. So I'm going to look at, we're going to start off with one that's pretty simple. 3 cosine of 4x. And the reason that we're going to do this, start off with one that's so simple, is because we've already kind of talked about what to do when our inside function has a derivative that is just a constant. So here, the derivative of 4x, or rather 4x prime, is equal to 4, which is just a constant. So what we've said is when that inside function has a derivative that's just a constant, we can just divide by that constant and then apply the known form. Well, our known form, if we recall, the integral of cosine x was positive sine x. So here we'll have 3/4 positive sine of 4x plus a constant, and that's my final answer. Now, technically what we're doing here is a mini substitution that we're just not writing out. So we're letting u equal to the thing inside the trig function, 4x, which makes our du 4 dx, which then results in the integral 3, the integral of cosine u. But notice I kind of have to multiply by 4 and divide by 4. So I'm also going to have that 1/4 on the outside, and then the 4 dx becomes my du. So we are kind of doing that substitution. We just don't have to write it out because the derivative was just a constant. Whew. What happens when the derivative is not just a constant and we actually do have to do the substitution? So let's look at the integral of 5x cubed secant squared of x to the 4th dx. So in this case, again, we want to let our u be the thing that's inside of the trig function. So we're going to let our u equal x to the 4th, which means that du is equal to 4x cubed dx. Now we've said that it can be helpful to bring constants to the outside of the integral. So I'm going to bring that 5 to the outside, have x cubed secant squared of x to the 4th dx. And I can see that I need to multiply by a 4 to get the 4x cubed. So then I'll also divide by the 4. And then I have that 4x cubed dx as my du. And I can see that this results in 5/4, the integral of secant squared of u du, which, even though it's not just a trig function, it's not just secant, it's secant squared, is a known form. We know that secant squared is the derivative of tangent. So in other words, we know therefore that the integral of secant squared is tangent. So this is 5/4 tangent of u plus c, which gives us 5/4 tangent of x to the 4th plus a constant, final answer. And this right here was just the small substitution that I did. Okay, let's just do one more of these Actually, we'll do 2 more of these, kind of thinking about some of the things we've talked about in the past in terms of the functions whose derivative end up in the denominator. So let's say that I were to look at, for example, cosecant of 1 over x, cotangent of 1 over x, all over x squared. In this case, it does not make sense to let our u be the denominator. X squared is not going to be helpful. The derivative of x squared is 2x. I don't have a 2x there, but I know that the derivative of 1 over x, hopefully you know, is minus 1 over x squared. So here, again, I'm letting my u be equal to the thing inside the trig function. So that's negative 1 over x dx. I'm sorry, negative 1 over x squared dx, my bad. So I have negative 1 over x squared down here, which means that up here I just need to multiply by a negative. I'm going to stick that as a negative 1, and then I'll put a negative 1 on the outside as well. So I can see negative 1 over x squared dx, that's my du. And when I rewrite this thing, I actually have that 1 over x, that's my u, in 2 different places. So what results is negative the integral of cosecant u, cotangent u, du. Guess what? Known form. What is cosecant u, cotangent u the derivative of? If we need to, we can go back and look at our list of known forms here. Oh, yeah, that's right. It's the derivative of negative cosecant of x. So down here, we'll have negative, and then the antiderivative, negative cosecant of u plus c. The negatives cancel out, leaving me with positive cosecant of 1 over x plus a constant for my final answer. Okay, so this last one is maybe going to be a little bit more challenging, or maybe not more challenging, but we're going to actually do it in 2 different ways, just to see that sometimes there are multiple ways to approach problems. Just got to be courageous when it comes to picking your u. So we're going to look at the integral of secant of 6 plus 2 root x over 4 root x dx. And before I even start this, I'm going to be like, oh, hey, look, there's that constant. Might as well just flip it on over to the outside of the integral. And when I do that, it's going to be 1/4, not 4, because that 4 is in the denominator. It stays in the denominator. So I will have secant of 6 plus 2 root x over the square root of x dx. Oops, sorry, guys. OneNote closing. Okay, so secant of 6 plus 2 root x over root x dx. Now my option 1 for this problem is to use my new idea of u that I just came up with right here. That u should be the thing inside of the trig function. So I'm going to let this be 6 plus 2 root x. And remember I've said that you should just memorize the derivative of root x. So this is going to be du is equal to 0 plus 2 times 1 over 2 root x dx. So in other words, du is 1 over root x dx. Now, if you're not comfortable with that derivative, you should get to the point where you are. But just so that you guys understand what happened here, 2 root x is the same thing as 2x to the 1/2. So then this is 2 times 1/2 x to the negative 1/2. We just brought it down and subtracted 1. So this gives us x to the negative 1/2, which is 1 over x to the 1/2, which is 1 over root x. Okay, so just a little side work for the derivative there. Now it turns out I don't have to multiply by anything because guess what? My 1 over root x is already there. That's my du. And then my u was that 6 plus 2 root x. So I can just replace that. 1 over 4, the integral of secant u du. And now this is one of the new ones that I just told you guys today, ln of secant x plus tangent x. We'll just look at it up here. The integral of secant, where did it go? Of secant x is equal to ln of secant plus tangent. So you should really get on memorizing that. So then down here, I will have 1/4 ln of secant u plus tangent u plus a constant, and I will replace my u back, 1/4 ln secant of 6 plus 2 root x plus tangent of 6 plus 2 root x plus c. All right, take a second, make sure that you guys understand this, and then I'm going to redo this exact same problem in a different way. So we're going to have an option 2 here for root x dx. My option 2 voila. Okay, option 2. Oops. So we've also seen that when a function contains a square root of x, it can be useful to let u just equal to the square root of x. So I'm going to start this by letting u equal to the square root of x. And when we do that, we're going to immediately square both sides to get u squared equals x, and then take the derivative to have 2u du is equal to dx. So this will be my substitution. And then that dx right there, oops, is going to be replaced with 2u du. And then when I see that square root of x, it shows up twice, that square root of x is going to become my u. So when I rewrite this thing, I'm going to have secant of 6 plus 2u over 4u. Dx is 2u du. And now what I see is that u in the denominator here actually cancels out with the u that I have right there. I can bring the 2 and the 4 to the outside and have secant of 6 plus 2u du. At this point, I could do another substitution, or I could recognize that the derivative of 6 plus 2u is just 2, which is just a constant. And when the derivative is just a constant, remember, we can just divide by that constant. So I'm going to have my 2 over 4, that's 1 over 2. Then I'm going to divide by that constant, 1 over 2, and apply the known form. So that's natural log of secant of 6 plus 2u plus tangent of 6 plus 2u. So I'm just applying the known form. I know the antiderivative of secant is ln of secant plus tangent. This time I'm evaluating at 6 plus 2u, so I've got 6 plus 2u in place of those x's, and I had to divide by 2 because that derivative was just a constant. Let's not forget our plus c. So then we'll have 1/4 natural log of secant of 6 plus 2u was the square root of x, so 2 root x, plus tangent of 6 plus 2 root x, absolute value, plus c, and this is my final answer. Notice it's exactly the same thing I got doing it the other way. So either of these methods is totally reasonable, a totally reasonable way to approach this problem. This second method I find useful because it's really helpful to get used to this doing u equals root x substitution. It shows up a lot, but also this idea of being able to just divide by a constant and apply the known form without doing the substitution is really, really key for quite a few things in terms of integration. It's going to help us to way more fluidly approach integration. All right, so here we have seen integrals where we're letting our u be the function inside of the trig function. I'll see you in the next video where we see substitution in a little bit of a different way.